Myself Dr. Vijayakumar, EC Department Associate Professor, Aditya University. Today we are going to see the spectral characteristics of random process. So at the end of this particular session, student will be able to learn the understanding the need of spectral characteristics of random process, and we also will be seeing the definition and properties of power spectral density. So already we know that the random process consists of two characteristics, temporal characteristics and spectral characteristics. In the earlier sessions we have seen the temporal characteristics. So in the temporal characteristics we have studied the correlation functions. So again, correlation functions are of two types. We have seen autocorrelation function and cross correlation function. So these two functions will be helpful in identifying the similarity in the random process. We have seen that autocorrelation function is useful for measuring the similarity in the same random process itself. Simply by delaying, we will verify with the reference random process whether there is a similarity or not. And cross correlation function is used for finding the amount of similarity between two different random processes, namely x of t and y of t. So this temporal characteristics gives you the measure of similarity, and also we can compute the average value, deviation from the average value, and correlation, all these things. Next we are going to see the spectral characteristics of random process. So when we are studying about the temporal characteristics, we are getting some bit of information. Sometimes that information will not be helpful for us for complete analysis of random process. So here, this spectral characteristics gives you a lot of information when compared with the temporal characteristics, and also we will see the relationship between the temporal characteristics and spectral characteristics. There is a relation which a transform relates the temporal characteristics and spectral characteristics. So the power spectral density is one of the spectral characteristic parameter which will be helpful in analyzing the random process. So power spectral density describes how the power of the random signal is distributed over different frequency components, and also it gives you the frequency domain representation of the random process, complementing its time domain description. So this power spectral density and spectral characteristics of random process are the fundamental tools which will be helpful in analyzing, modeling and optimizing the signals and systems in communication, control and signal processing applications. So in almost all applications we use the spectral characteristics concept. So one of the important parameter in spectral characteristics is power spectral density, which help us to know the amount of power stored over a wide range of frequency component, and how the variation of the power, all these things we can study from the power spectral density. So clearly gives you the power spectrum. Power spectral density estimates the power of a signal at different frequency component, which frequency component is dominating and which frequency component holds the high power and which frequency components holds the low power and which frequency components covers most of the power. So all these things we can clearly visually we can see in the power spectral density plot. So this spectral analysis is a process of estimating the power spectrum from its time domain representation. From the temporal characteristics we can get the spectral characteristics just by applying Fourier transform. We will see the relations in the coming topics. So the spectral density characteristics gives you the frequency content of the random process or stochastic process. So it will decompose the signal into stochastic process and identify the different frequencies and identify its periodicities, which is very helpful in analysis of the signals. So the widely used instrument for performing the spectral analysis is spectrum analyzer. So the spectrum analyzer gives you the power spectral density parameter, how the power is distributed among the different frequency components. So just now I told that what is the importance of the spectral characteristics. What is the importance of spectral characteristics? We have seen the time domain characteristics or temporal characteristics. So see here, assume a person is somewhere staying in time domain, assume another person is staying in frequency domain. So assume a white light is passed through a prism. We know that the prism will split the white light into Wavejoy. It will divide the white light into 7 colors. So the frequency domain person will have some bit of idea that a white light is a combination of 7 different frequency components. But a time domain person don't have absolutely no idea what white light consists of. He got only little bit of information, whereas the person standing in frequency domain got a more information. So any analysis which we will do is to extract more and more information. So now you can see here clearly the frequency domain characteristics or spectral domain characteristics is providing more relevant information, in particular more relevant information which will be helpful in experimental analysis. So this frequency domain analysis gives you additional information when compared to time domain analysis. That's the main idea why we are moving or why we are studying the spectral characteristics of random process. So definitely to extract the additional information, we are going for spectral characteristics. So to analyze a random process simply in time domain doesn't give us more information. So we need to analyze the same thing in spectral domain also. So the one of the important parameter in spectral domain is power spectral density. So already we mentioned the definition of power spectral density. Power spectral density gives you the amount of power distributed over different frequency components. Particularly we are talking about random process. For a random signal, how the power is being distributed is given by power spectral density. So there is a mathematical formula for power spectral density. The mathematical formula is this one. And power spectral density, if it is auto power spectral density, we are computing the power spectral density for the same random process. Generally, it is denoted with the symbol Sxx of omega. That means in same random process, I am computing the power spectral density. Limit t tends to infinity, expectation of xt of omega whole square divided by 2t, where xt of omega is nothing but the Fourier transform of the band limited signal over a time interval minus t to t, and t is the time period which is of interest. So this is the formula for power spectral density. Okay. And also I mentioned that we will see the relationship between temporal characteristics and spectral characteristics. One of the temporal characteristics we have seen is autocorrelation function, and the power spectral density is the spectral characteristics. These two are interrelated to each other with the help of a Fourier transform. So power spectral density and autocorrelation function form a Fourier transform pair. If you know the autocorrelation function, you can compute the power spectral density, or else if you know the power spectral density, you can compute the autocorrelation function. Both is possible. So simply by applying Fourier transform and inverse Fourier transform. We will see the derivation and how this relation is obtained in the coming slides. Next one, average power. Average power. We can compute the average power simply by doing the time average, and we are multiplying it over a time period. So the power spectral density, if you compute over a particular time period, it gives you the average power. This is the mathematical formula for computing the average power, or average power is otherwise defined as second moment of the random process, time average, second moment of the random process. So we have seen this particular property in autocorrelation function. Autocorrelation function at tau is equal to 0 gives you the average power. Autocorrelation function at tau is equal to 0 gives you the average power. This is one formula to compute the average power, integrating the power spectral density over a frequency band. The frequency band is d omega. It can be omega 2 minus omega 1. Okay. This gives you the average power. Other way to calculate the average power, autocorrelation function at tau is equal to 0. Or simply the mathematical definition for average power is second moment of the time average, second moment of the random process. So all these three formulas are valid formulas for computing the average power of a random process. So we will see the properties of random process, which will be helpful in computing the problems and which will be helpful in understanding the relationship between temporal and spectral characteristics, and some properties will be helpful in computing other parameters like average power and autocorrelation function. So we know that wide sense stationary process, everything here we are taking a random process as a wide sense stationary process. for a wide sense stationary random process, if you compute the power spectral density, the power spectral density is always greater than or equal to 0. That means it itself is a positive quantity. The power spectral density can't be a negative value. Next, the power spectral density at 0 frequency. The power spectral density at 0 frequency is equal to the area under autocorrelation function. Area under the curve of autocorrelation function. So, this is from the relationship between power spectral density and autocorrelation function. Simply you substitute omega is equal to 0, you will get the area under autocorrelation function, which gives you the power spectral density at origin. Next, power spectral density is an even function of omega. Even function of omega. We know that what is meant by an even function. F of minus x is equal to f of x. So, similarly here Sxx of minus omega is equal to Sx of omega. So, it is a even function of omega, and the power spectral density is always a real function. And few more properties are there. The time average of mean square value of wide sense stationary random process is equal to area under curve of power spectral density. So, which is nothing but power, average power, which is nothing but average power. Already we have seen the mathematical formula for average power. Average power, how do you get average power? Area under power spectral density with respect to frequency gives you average power. And there is one more property. So, if you do the derivative, and which is numerically equal to omega square into Sxx of omega. This is one property, and the final property, very important property, Wiener-Kinchy relation, which relates the temporal characteristics with spectral characteristics. So, we already mentioned that the Fourier transform of autocorrelation function gives you the power spectral density. Let us see the derivation part. Okay. Before that, we will see small proofs. The power spectral density at omega equal to 0 is nothing but area under autocorrelation function. This is very easy, you can prove very easily simply from the Fourier transform pair relation, and average power is mathematically equal to area under power spectral density, with respect to frequency. And we know that the power spectral density is always a positive quantity for all frequencies, and power spectral density is also a even function, So, Sxx of minus omega is equal to Sxx of omega. Omega is 2 pi f, sometimes we represent simply as Sxx of f. So, Sxx of minus f, just I am substituting minus f here. Now, what I am doing is, I am replacing tau with minus tau. Then the relation will be something like this. We know that autocorrelation function is an even function. So, Rxx of minus tau will become Rxx of tau. So, which is mathematically equal to Sxx of f. So, Sxx of minus f is equal to Sxx of f, even function. So, generally it is symmetric about y-axis, You can see here the right portion and left portion both are equal here also. So, even function of omega. Now, let us see the important relation. Every time we are using power spectral density and autocorrelation function are Fourier transform pairs. So, let us see the derivation of Fourier transform pairs relation. Okay. So, firstly I am taking an x of t, which is a random process. I am time limiting it to over a range minus t to t. I am redefining it as xt of t, and the Fourier transform of xt of t is xt of j omega. And we know the Parseval's theorem. In the Fourier transform, we use this property quite regularly. Parseval's theorem relates the energy and energy spectral density. So, from that, this is equal to this area is equal to this area. So, the average power is equal to 1 by 2t minus t to t x square of t, which is equal to 1 by 2 pi minus infinity to infinity xt of j omega whole square. So, see here, xt of j omega is minus t to t xt of t e power minus j omega t, and we know the Sxx of omega is mathematically equal to, this is the mathematical definition of Sxx of omega, expectation of xt of j omega whole square divided by 2t. So, we are using that relation for 1 xt of j omega x of t1 e power j omega t1 x of t2 e power minus j omega 2. Since they are complex conjugate, s into s star is equal to s square. So, assume this as a complex quantity, this as a real quantity. Now, applying the expectation of x of t1 into x of t2 is autocorrelation function. So, we replaced it with autocorrelation function. Now, we are applying the inverse Fourier transform on both sides. F inverse of sxx of omega is equal to, so applying the inverse Fourier transform, this is the inverse Fourier transform for sxx of omega. Applying here inverse Fourier transform, see here 1 by 2 pi, and this part is mathematically equal to shifted version of impulse function. 2 pi cancels out, delta of t2 minus t1 minus tau. We know that the impulse function is defined only over the range minus t2 t. So, which is equal to rxx of t1 comma t1 plus tau. So, this is equal to time average autocorrelation function. So, the inverse Fourier transform of power spectral density is equal to time average autocorrelation function, or power spectral density is the Fourier transform of time average autocorrelation function. So, in this session what we have seen the summary, what is the need of spectral characteristics of random process, and we defined what is meant by power spectrum mathematically and theoretically, and we have seen the properties of power spectral density. So, in the next session we will be seeing the problems in power spectral density. We will apply the properties of power spectral density in solving the problems, in computing the parameters. Thank you.